So, okay. Do you have any questions yesterday? Neil and then you were asking questions and say, okay, let's answer it tomorrow. You don't remember the question. Okay. What is a brush and a brushless motor? Actually, there is a huge, huge difference in the mechanical part and also in how you control these influences. For that, I think it's better that we can open up a stepper motor, for example, and we can open up also a DC motor. But let's first do this. So I'm looking some images. This brushless versus brushed motor. These both a brushless could be in runner and out runner, and in general, all the brushed are in runner. In general, most of them. So the difference, if you want to, this is not the clearest example. Okay, this one is a really good example. Is in this case, both are in runner motors. The part that rotates is inside. And in this case, the part that rotates is inside. In one case, we rotate the coils, and in the other one, we rotate the magnets. To rotate the magnet, we don't need to make any electrical contact in the magnet because the electrical contact is on the coils. So if the coils are fixed, just by changing the current through the coils, it will rotate the magnet. Meanwhile, on the left, that is what we consider a standard DC motor, what we do is we don't change, we don't move the magnet. The magnets are fixed in the outer casing of the motor. As for example, this DC motor, I need to see myself on the camera. Sorry. How I can pin myself. Pin? Yeah. So in this case, this DC motor is a standard DC motor. This one has a reduction gear, but we have the metal sleeve and the plastic cover. It's because we are rotating the coils. The coils rotate. In order to change the polarity of the coil, how we do it? We have two metal connectors, two metal, actually brushes. It's a metallic brush, one here and one here. And the coil of, let's change the color of each one. One is wired, sorry, bad color. Let's take red or yellow. Actually, the coil of one goes like this, and the coil of the other one, this is a really bad color, sorry. So one coil basically goes like this, and the other coil goes like this. And we have two metallic brushes touching, in this case, this and this side. So if you rotate the motor rotates. If this is positive and this is negative, when you rotate, this guy becomes negative and this guy becomes positive. So actually we don't change the polarity on the power source. We don't control. We just have a steady positive and a steady negative. What it does is it change the motor connection. So actually that's how we invert the current mechanically by changing the position of the coil. If you look for a closer and more detailed schematic on how it is, it's brushes. They look like this. What is this example? Yeah, here. they look like this. So actually, this will be one connection of the coil, and the opposite in the other side is the other connection, the positive and the negative. And here, this one is negative, and this one is again positive. So actually, it's changing. By changing the rotation, you are changing the contact zone from positive or negative of the coil. Is it clear? Really? Not a lot?
In Spanish, probably you heard it over escobilla, and it's the most common problem because at the end it's picture that is transmitting electricity and they wear out and they stop making contact. And just think of this idea we were talking yesterday. We have permanent magnetic field that doesn't change. These are the ferromagnetic elements. Then something that we have to constantly invert. And we can do that with HVG, with those circuits with transistors or things like that, or we can just do it mechanically. And in the brush DC motors, which are, let's say, less technologically advanced, done mechanically.
So
it makes more sense development point of view in principle, right? So if you don't have electronics, you just have control of the motors in a mechanical.
So this is the super simplified schematic on how it is. You have half cylinder, one polarity, half cylinder, the other polarity. It just conduct electricity. This will create the magnetic field. In this case, this one get repulsed from the positive, like if this is south and this is south, it will get repulsed. It will try to get out. It will rotate and attracting it. By rotating, change actually the connection polarity, making again another field that is repulsing again from those north or positive, and it's an infinite loop. Actually, this is the simplest motor. You can make this one with a battery. Actually, last year we had a little class on how to make your DIY outputs, that you can do it with coils and batteries. That is exactly how to make that. It's quite simple. In this case, it's not a brushed, it just continues in the same polarity, but as you have inertia of the coil, it keeps rotating. There are other ways of doing this, or actually how to make them, but follow the same concept. In this case, for example, the test we did at home, and finally the wire burned because it was not the correct length. So the problem with brushed motors are the simplest one to use. You just connect positive and negative. They usually tend to have a positive and a negative. You will say, but it's the same coil. It doesn't matter the direction. It's just a piece of cable. Yes, actually it matters. Why? Because of the brush design. Most of the DC motors, they have the brushes designed in a certain position. So actually, if we draw a good, let's say, a 4 sides commuter is this part. Usually has like this. For one coil, actually, let's draw it with colors. Might be easier. This is the commuter. This will be the positive and the negative. And we have the other commuter that is the negative and the positive. And you will have two brushes that is basically a really thin metal plate for the positive and a really thin, let's think, this is black, okay, but I cannot make it black. And a thin metal one for the negative. As we have metal with metal in friction, we use what is called the brush, cepillo, escobilla in Spanish. That this is a hardened metal, piece of metal with quite a small amount of friction that might eventually wear. And this is actually what gives the due life of the motor. In huge motors, this place could be replaced. In small motors that are like cheap enough, we directly dispose the motor completely. But for example, a handheld router The ones that you use for like finishing the wood, etc. Those are basically a DC motor. These ones are these mechanically apparatus are expensive. A good handheld rotor is 200 euros. There is a little door that you can open. There is a spring and something that is the brush that you can take out and replace for new ones. They're rich in this replacement. For more or less in serious motors, you have these brushes. In small scale motors, this is a metal plate that is just resin and pushing to the inside to keep the constant contact. So these guys need to be replaced, and eventually they slowly get tear down. And for example, when you see a motor that is making sparkles continuously, like when you start a DC motor, usually can actually make sparkles. It's normal. If you're over exceeding the rotation speed, it might eventually you see some sparkles coming out of here because there's not too much friction and too much heat, and actually you're destroying too fast the brushes. That's what's happening. Happens a lot also that if this brush has turned down, you're basically making contact with the plate. Why we say that DC motors have and not have actually polarity and connections? Because of these guys. If you rotate this motor in this direction, the brush usually tends to be slightly tilted. So actually it doesn't get trapped with this space. That's actually why the DC motors are in general designed to rotate in one direction. Some DC motors, they don't have polarity, and it's because they have like more or less an even brush design that allows them to rotate in both directions. Usually happens, for example, this DC motor design is usually meant to rotate in only one direction. Why? Because these metal plates are stronger counterclockwise than clockwise. For another standard type of DC motor will be something that is similar but not exactly the same. Let's say this is another coil, and you have your brushes. I will design it horizontally nowadays, right now. And these guys are encapsulated in a metal sleeve, and basically it's a cylinder or rectangular space. And how you push these guys is actually you have a spring just keeping the pressure on the brush. So these guys, not all, but in general, they are more prone to rotate in both directions than these guys. That's why most of the DC motors, if you look on the camera, they are marked, and usually not in the simplest way. Okay. Okay. So in general, the positive of the motors is marked with a little dot. In this case, it doesn't have even color. It's just a package design. Other DC motors, this one is wasted. Well, what you can see here, there is a red dot behind the cover. That means this one is for connecting the positive. So those ones you should connect always with that polarity. You can run them in reverse, yes, but they will last less time, way more less time.
Explain yesterday how they start, in which direction they will start, but I don't remember.
This is about how the commuter is designed and the version design. They tend to always start in that direction.
Okay.
It's about how they make the contact between the commuter parts.
Okay.
But theoretically, a DC motor in this case can either start to the top or to the bottom one. This like simpler theoretical motor could start both in both directions. It just depends in the initial impulse or if it's just 1 degree more in one direction than in the other one. But just because of casing design, brusset design, commuter design, they usually they automatically turn in one of the directions. Okay, this is about brushless. Brushless, how you move. You have a magnetic as a free wheel. Basically, this has no other friction than the own friction of the bearings that is holding it in place. Of course, brushless motors are more efficient. There are no friction. Like if this guy has the friction of the brushes plus the shaft friction that could be held in place by a bearing, this one has only the bearing friction. So actually, this one wins because it has less friction. That makes it more efficient. What else? As less friction, usually they speed up faster and accelerate faster, and they have higher speed because they are not mechanically constrained by the brushes. They are constrained by the bearing dimension and how the bearings are designed. So in general, these ones are better in everything. What happened? Price. Why? It's not directly on the motor design. Actually, these designs are cheaper to manufacture. What happened is you need electronic control. To what? To change the polarity of the coils. So these ones, you don't need any electronics to control them. You can just power current. These guys, you need actually to change the current direction. So by so, you put a layer of electronics on top to be able to control them. We can have brushless DC motors. For example, a stepper. Teníamos otro stepper por aquí abierto. Sí. So in this case, for example, this, let's make it big. ¿Me puedes pinear en la pantalla? So in this case, for example, this is a brushless DC motor. What is the part that rotates? The inner core. That is this one. That is basically is a free wheel on two bearings. So there is almost no friction. I just make a small movement and keep rotating quite a lot. These guys are the magnets, and you can see each little line is a different change of polarity of the magnet. And you can see on the side that actually they are not aligned, all of them, to each other. This is to actually control the change of rotation. This is one of the things that makes start in one direction or the other. And here we have actually the 200 steps for the full rotation, and we have the coils. This is a stepper. So actually these are two DC motors, will be the vertical one, then we have coil A, coil B, coil A, coil B, coil A. So actually this is a double DC brushless motor, but it's called a stepper. Then we have BLDCs. That is what we normally know as brushless DC motors. That is another completely different league that we didn't went through it yesterday. Before going into that, let's open up a little DC motor. They are so cheap that.
No hay alguno de los de.
No, there is nothing in the chat. No, just. So, for example, this is the coil. This is the part that rotates on the motor, and we can see the polarities and the coil. And here we can see the commutator that you see is black and like in theory is copper, but has these little lines. This cylinder that you see coming out is the commutator. And you can see how the coils are attached to, is it difficult to show on the camera? Let me, I think it's better if you just put the white background constantly on it.
No, this one.
No, I think just that. Okay, way better. So actually you can see how the coil here is getting in contact with this part of the commutator. And this coil is getting in touch with this part of the commutator. How these guys attach to? This is actually a brush contact, the super simple one. We have a metal flexible sleeve, and these are the brushes. So actually these are the parts that were down. And that's why also all you see all this dust and black residues are become of the leftover of the brush. Actually, to fix these guys and to reassemble again, we need to open up. Really not that straightforward. Yep. So now, let's see in which position we can light up. We can see that the brush changes the direction of rotation. And change the contact zone on the brush. Brushless. Brushless is a completely different story. Completely. They are not either a DC motor, standard brush DC motor, neither a brushless DC dual motor that is a stepper. We have a motor that is the most efficient one, is the most powered by weight of all of them, is quite simple to manufacture them, but we have a high level of electronics in order to control them.
It's more complicated than stepper motor.
Way more complicated.
And more expensive.
Now they are quite cheap, but still they are complicated to control. We need to be really fast in order to control. So we need really high frequency control. So brushless design, what we call BLDC, brushless motor DC, has 3 cables. You say 3 cables? Why? Where is the missing one? Okay, because the design is in star. So we have one coil that is getting to a center connection, another coil that gets to a center connection, and we have another coil that gets to a center connection. And actually, how we control is everything about timing. So we first have a phase that this one is positive and this one is negative. So the current flows in this direction. Then we have a second phase that this becomes positive and this becomes negative, and the current flows in this direction. And then we have a third phase that this becomes positive and this becomes negative, and the current flows in this direction. Can you guess the motor direction? Actually, it's opposite. So this is the it's even difficult to find. This is the simplest schematic. These ones usually are in like 6-star configuration. You have 6 coils, each one crossed to each other. And you have to wire A, B, C, A, B, C, A, B, C. And then you have A, C, B, B, C, B, A. and they change the coil. Depends. There are 3 different types of wiring for these motors. But these motors, as we are changing the polarity of each cable, what we need to control them. If we just have a coil and we want to change the polarity of them, what we need? An H-bridge. If we have 2 coils and we want to change the polarity of them, what we need? 2 H-bridges. What is this? A stepper. If we have, let's say, one coil that both change direction, we need actually 3 H-bridges to control them. And this is about timing, control of the brushless, and how you start. The timing is not constant all the time. Usually change depends on the speed revolution. You have acceleration curve of timing. So actually we don't have a steady control that we are changing all the time the same speed. In order to change the speed variation, what we have is we generate pulses, shorter or longer. And what is this? PWM. So actually these 8 bridges are controlled by PWM. That pulls a lot of layer of complexity in electronics. But at the same time, that's why before they were more difficult to control. This we have a, in general, we have H bridge, H bridge, H bridge, and we have its own microcontroller that is managing the connections, because this is a double H bridge, so it means we need 4 cables for each one to control the 4 change of transistor. Each one with PWM control. So this is what we call as electronic speed controller, also called ESC. So this is a layer of electronics that in this case is, for example, this is a brushless motor in runner, because this one rotates in runner, and this is the electronic speed controller. What is inside here? Actually, exactly this model, I know that is a 80 mega 328. It's the same microcontroller that runs the Arduino. But this one is a small, like all the pieces of Arduino. Just we have pins for programming it. ESP connector. We have, if we open the stick, we can see the ESP connector. Actually, I think ESP, the programming for SPI, no, ESP, Java ESP. ISP, sorry. Sorry. So actually, like I don't use this guy, so let's open it. Let's clear the drawing and let's stop sharing so you can see the camera. Let's see what is inside here. So for example, here we can see different things. First, we have in one side, we have 3 cables. That is for the motor control, the 3 phases. In the other side, we have a quite thick cables This is a really small device. This is measured like 1 by 2 centimeters. There we have two thick cables for positive and negative, and then we have really thin cables that is positive, negative, and data. So actually, these guys is the power connector directly from the power source, the battery, and this one is what we use to control them with our microcontroller. The black is always mandatory because they need to share ground, and the white is the data one. The red, we will see later why we have in this one. We have a huge capacitor. For the size, this is a huge capacitor. It's almost the same size as the board. Why? These brushless, they are really efficient, but also they are really efficient, and we can make them really, they have a lot of power per weight ratio and per size. They are really power demanding in general. And this especially is designed for like being able to hold 10 amperes. So 10 amperes is crazy amount of power, and all this device can handle it continuously. And actually, this one, I know in peak can handle 15 amperes for 10 seconds. So what we have here, we have.
Sorry, the capacitor, what is it?
When the power source cannot deliver that amount of power, the capacitor comes into rescue.
It's always loaded. From time to time.
When the power gets down, because there is a power above the maximum output of the possible battery of the power supply, the capacitor helps to actually take that amount of extra load as necessary. That might be, for example, a acceleration or a peak in the torque, etc. And usually these ones are quite close to what is power demanding. What is power demanding? The MOSFETs. The H bridges that are the MOSFETs, that are the ones that actually give the power to the. So here, for example, we have an 80 mega 328, but this is the smaller package, just to make it simple. And these guys that you see here are the ISP connectors, ESP connectors to actually program it. And then we have like this is the crystal, the same as we have for any microcontroller of this size. And this guy, I don't know, might be a transistor to actually help managing the power. What we have in the other side? The triple H bridges, in this case, for like on hardware design, we can see one cable, two cables, and three cables. This is about Oscar knows more or this, but in this case, why we have, for example, one of the cables with instead of 1 H bridge, that is why we need 2 H bridges. They are connected in parallel. So actually, if this bridge is rated for 5 amperes and this bridge is connected in 5 amperes, they both add 10 amperes. So instead of go to a bigger package that might be more difficult to dissipate the heat because they don't have more surface area, we go to smaller packages and we distribute loads in parallel.
The word synchronized?
Yep. I don't know how easy it is to design this synchronization of H bridges, but this for speed controllers is usually how they do. And in case of larger packages as this one, all this area that is actually a metal plate behind, I think there are 4 H bridges for each side. And we have the one line of H bridges and the other line of H bridges. The good point of these guys is we don't need to actually design it. Like, it doesn't make any sense. Once they are programmed to know the timing. Usually these guys run their own firmware that tells the timing. You can have the timing of 1 millisecond or 2 milliseconds, 3 milliseconds. You can establish power declaration curve and other things that we will go. But let's go for the basics. So ESCs are rated on different things. First is maximum amperes on hold. Means in current, continuous current. This one is 10 amps. If we go to the data sheet, I just remember this one because I have a lot of them. This one is 12, 15 amperes. Usually for 2-3 seconds, maximum 5 seconds, they establish how much time. Usually you choose these guys to be around 20% less than the maximum power consumption of your motor. So if your motor is 8 amps, you choose a 10 amp speed controller. If you have a 80 amps motor, you choose at least a 100 amps speed controller. Why? Basically, these guys get hot, quite hot. It's important to have a proper cooling of these guys. Then we have working voltage. Actually, this speed controller is an H-bridge. The H-bridges are rated the same as a MOSFET. A MOSFET has a maximum working voltage and a minimum one, no? So, for example, yesterday we were seeing that a MOSFET could be rated between 3 volts up to 36 volts. So in this case, it's the same. These MOSFETs are rated from 5.6 to 16.8 volts on working current. And then we have a BEC. This is not that common in all the speed controllers. BEC stands for es el transformador de energía, bulk converter energy, puede ser algo eso. Bulk energy converter, yes, exactly. So basically, this means that the power coming through these guys, through the main battery one, this speed controller also regulates power back into a 5-volt line. A 5-volt. So actually, you see this data line. Let me show it. This one, we can actually just power directly the speed controller and have our microcontroller connected with these 3 guys, and this one will feed all the electricity needed for a microcontroller. We don't need to power our microcontroller separately. So actually, this works at the same time as a regulator. And this one, it says that this buck converter can output a maximum of 2 amps at 5 volts. Not all speed controllers have BEC. That means this device not only controls the motor, but also helps because reduces one element in your electronic design. We don't need to have any power regulator. This one is doing everything already for us. It's a 2-in-1 package.
Because beside the motor, for example, can be
yes, but this is on this side. It's on the motor side. On this side that you see the cables are quite thin, is because in order to control this guy, we need a white cable that is the data. That for controlling speed controls, we use PWM. Yes, we have a ground that we always need to have it shared, and a positive that in this case we have white because this speed controller has a BEC. Other speed controllers, for example, this one, doesn't have red cable. Why? This is a speed controller without BEC. So actually, you need to power your microcontroller individually, independently. Why you have like this and why you have like this? Having a BEC simplifies your possible circuits. The ones that are black and white only ground and data, in general, they tend to be what is called opto-isolated. And what is a opto-isolation? Oscar? Exactly. So that means that in our circuit, how I can draw here. In our circuit, we will have the motor that has 3 cables. We will have the H bridges. We have the peak that is controlling them. This is all encased in the speed controller. This is the speed controller. This is the motor. Here we have our board, whatever it is, that is generating a PWM to control it, and has also a ground connection. And this guy is being fed by a super thick cables of positive and negative. This is a speed controller. Actually, isolated is when these signals, these two cables, actually are not connected with a wire directly. We have what we have is a emitting diode, and here we have a sensor to actually receive the pulses. So instead of having the pulses in electricity, we just have a little flashlight and a sensor measuring the flashlight. So as we have electrical separation, galvanic isolation, we will not have noise, electrical noise. Why? Think about what are the ratings of these guys in general. Even the smallest motor is huge. We are working in general with like high voltages and high currents. That means in general, and we are changing the direction of the current multiple times, actually like around 1,000 times per second. If we have a super steady control electricity, the variation of this creates magnetic fields. By so, creates electrical noise on the signals. If we have too much of this electrical noise, this can come back, but electromagnetic field interference into the data lines and confuse our board. So actually, we want to have them all opto-isolated. In the moment you have like high power devices, in general, you want to have everything opto-isolated. So there is no noise coming back between the different devices of the system. And that's why we have standard ESCs and ESCs that they just say opto-isolated. Of course, these ones are better. But as they are opto, what we never have with the opto-isolated ones, power going through them. They never have a back, because if not, you could not be opto-isolated.
The E and the E is electronic. Okay.
Electronic speed controller. Yes.
Just a question about like basic electric consumption. Just to understand from what you said yesterday, when you said that the rating voltage of the ESC you showed was from 5 to 16 volts, so it means the battery benefits. It's the voltage of the battery, no?
The voltage, the battery, whatever the battery you connect, needs to be higher than 5.6 and maximum of 16.8.
And so this voltage is representative of the maximum speed that the motor will reach.
Okay, that is motor design.
We will talk about that?
No, just right now.
Okay.
It's actually a good. Did you got the speed controller? Okay.
They're only DC motors for the
The speed controllers are, the ESCs are only used with brushless DC motors. For a standard DC motor, we don't call them ESCs, we call them variators. What is a variator? Like that in general we don't have, is something that varies the voltage. If your battery is 10 volts, but you want to change the speed electronically, you basically have a kind of, it's a MOSFET with a board that controls the voltage range. Transform your digital into an analog output.
Related to that, we said that the motor cannot take more than some amps. So you say, okay, I will give him like maximum 12 volts of each speed. And we say that its maximum current is, I don't know, 5 amperes. It's 5 amperes, if you put more, it will melt.
That's it.
Okay.
So actually, brushless is funny, but they have like 3 different numbers. They are rated, the first brown color, first 2 numbers is the size in diameter of the stator. What is the stator? Is the coil size. Could be inside or outside. Okay, this is a little bit messy because changing in runners and out runners. But stator, BLDC. The stator is this. Is the coiling. So the dimensions of the brushless motor is diameter of the stator and height of the stator is the second range of numbers. So actually in this motor, we have 22 millimeters of diameter of stator, 0.4 on the height. More diameters, what we have, a wider motor, in general more torque. Higher the motor, but in general also lower speeds. Why? Because we have more inertia. And that also leads to a motor that in general accelerates slower than one that is thin. Like we have torque on the motor, that basically implies maximum torque. Thicker motors, more torque. Thinner motors, less torque, but in general also more RPMs. More RPMs because we have less inertia of mass of rotation. Why? Because in front of each coil or each stator, you have the magnets. That in general, for designing most of the brushless motors, you use really good quality magnets, and this is what is called neodymium magnets. I don't want to mess up too much into this, but brushless, they can become really complex on the designs. You have like really few coils, or you have multiple coils with thick or thin cables, depends on the RPM, etc. But the number that you need to look for is the number. They will state the size. And then they have, this is wrong. This is not kilowatts. This name is really wrong. This is kV. K's per volt, means rotations per volt. This is the maximum speed of rotation of the motor and the minimum one. Let's say you know that you will power your motor with a 12-volt battery. What is the speed of rotation of this motor in what we call in the air? Is no load on it, like completely free wheel. We multiply 12 by 2,300. So actually this motor 12 per rotates at 27,000 RPM in empty, in the space, in the air.
What was the issue for
B2 is, this is just the naming that they put to this motor in this case. So for getting any brushless motor, you have data sheets almost always, and they tell you, for example, in this case, this is a motor designed for drones, so actually it's for a propeller size. This one, they say, okay, this motor with this propeller, with this size of propeller at 11 volts, will have a minimum, let's say at the slowest speed, a 0.8 power consumption to 13 amps power consumption. And in this case, it will push 400 grams of air, will be able to lift 400 grams. This is, for example, how to specify a drone motor or aeronautical motor, brushless motor. But other brushes, brushless design, what they do is newtons per meter. That is the same. Basically, what we have a propeller is a arm, direction, and friction with air. But these ones, they just state. And they have the power, total watts of power. So a normal data sheet of a brushless DC motor is, they say, max amperes, max watts, and Newton per meter on torque at a certain RPM.
of this table is for 1 RPM, like on max RPM or max.
This one, the maximum power consumption is at the maximum RPM. This one is at the minimum RPM. What is a minimum RPM of a brushless? 0 voltage going through it. Because we have coils, if we don't put any voltage, we can actually do the timing with 1 volt. Or we can do the timing with 12 volts. Actually, changing the voltage, what will change the speed? The motor being stopped is 0 volts.
Why at 11.1 volts, you don't have the maximum speed?
Because this is about battery design. This in this case, this is a table datasheet specified for, in this case, for a nautical. So in this case, they assume you go automatically into batteries, and this is about LiPo batteries and Li-ion batteries. Let's say any battery, even if it states 12 volts, the battery is never 12 volts. When it's at the maximum load, usually they're around like 12 point something. Could be 2, 3, 6, even 13 volts. And when they are discharged, they could be usually 9 volts. So actually what we have with 12, or usually is 11 point something, is the mid range of the battery. So a battery is never exactly 9 volts or 12 volts. It's around that area. Except actually the alkaline batteries, the AA batteries, they say 1.5 because it's the load when they are fully charged. When the battery is almost discharged, it's 1.0. Then that is when you have to dispose the battery. Rechargeable batteries, they have a working voltage range between the min and the maximum, when they are discharged and when they are not discharged. A battery with 0 volts is a dead battery, always, like it's a damaged battery. Oscar, algo que se me olvide. Sí, tranquilo. So these guys, for example, you can find them in really, really high speed and or really slow. Actually, you have these motors that they can actually, for example, Victor with Romy, the mod is doing the cable bot, is using a brushless, a really thick and high brushless, a really thick and high brushless, actually that looks quite similar to this in size, but it's half the weight and has a lot of torque. And he has the kV of that motor, I think it's like 60. Because actually each movement is going to move a lot in the cable. Basically, it's the roller wheel of the cable. The casing of the motor is the roller wheel. So actually, you are able to move slowly with that motor, but with a lot of torque. It's really efficient. Usually, also the lower the kV, the motors tend to be more and more efficient. The higher the kV, the less efficient they are. Also, these ones, for example, they state in this case they don't state, but they have another lineup where they state the efficiency. At which revolutions this motor is more efficient, because it usually is efficient around 70% of the maximum load of the motor. What happens when you go above the maximum amperes consumption of the motor? The amperes automatically relates to the watts. But it's basically electricity transformed into movement and peak, and if it's not translated into movement, it's translated into what? Into heat. That is about the heat is dissipated by the copper coil. The copper coil has a resin cover over them, so they don't make a shortcut. When the coil has reached the maximum amount of joules per second, or I don't know what's the unit, but the maximum dissipation power that this coil can have to the exterior, what we consider 25 degrees air, basically they start overheating and rising the temperature. So the temperature rises, and nothing to stop because it cannot dissipate the power. So actually that reaches the melting point of the resin and makes a shortcut. And then is when you have the black smoke of the motor. So actually the motors might get hot, but there is and this is actually usually the maximum rating is below the maximum threshold of the resin that is determined by the batch dissipation power of the motor. For example, let's go to Hobby King. Let's look for some brushless motors and see the data sheet. Hobby King is a hobby store that they sell a lot of types of brushless DC motors. Really good quality ones and also normal quality and some of them bad quality. There are a lot of them. I hate the website, it's super buggy, but they have good. Okay, motors electrical, brushless. So for example, here in this case, you have different cases, but they are all the same. For example, this one, NT drop drive.
What is the sensor? Sensor?
What is?
The first one, they say sensor, brushless motor, the sensor. What is it for? Is it about an encoder?
Hall sensors. Okay, let's that's the next generation of this wireless DC motor. Wait for a second. So actually, this one, for example, is a outrunner. The casing is rotating outside. Usually, they also state the, for example, this one says that it's a 35 millimeter on the width, 48 millimeter on the stator height, 1,100 kilovolts. The maximum volts are cell count. They don't say volts, they say cell count. This is a terminology for batteries. Battery. I will go in deep. It will go in deep now, but this basically means 16 volts. And we have a recommended speed controller between 80 and 100 amps. Maximum current of the motor is 70. But that doesn't mean that if you go at 71, it will burn. For example, if you have a really cold environment, you have this motor in the Arctic, probably you can go up to 100 amperes without burning it. So the same also having the motor in stop that having with air running through it assisted, because you basically are cooling the motor. Also, it's not the same. You can run, for example, 100 amps for 1-2 seconds. That doesn't produce enough heat to actually burn it out. So this one is maximum current, continuous current, 70 amps of continuous current, sustained current. And they state more things. In general, they have data sheets that you can download. I don't know where they are, but should be around it. I need to register in order to get them. This is new. Before you even get the So these motors are quite good. Like they're best. They are the best ones. But if we go again to the basics, what's happening when you run current through this guy? Sorry, this is negative. You can actually use this guy for another purpose. Meanwhile, when we generate a magnetic field, what is happening with this guy? A side effect is also generating another magnetic field that this is called EMF. Electromagnetic field generated because of the other close by coil. So new generations of speed controllers The 8 reaches are not just one direction to the motor. They all can also sense back. So actually, if we measure this back EMF, we can have position control. And actually, this is, I know it can be done. I don't have any idea how they do it.
And why was position control for models and so fast?
But not all the browsers goes fast.
Okay.
Actually, a browser can have no movement or just 1 degree movement, the same as a stepper motor. So actually, with these guys, you can have back EMF readings to actually estimate, because this is an estimation as you are not using a, let's say sensor embedded into the control, into the motor. You are using the electromagnetic fields interference between the motor to actually read the position and estimate what exactly the position of the motor. And actually, you have really close right now. This is getting really good, and it's super accurate control. So actually, we don't need to make this hardware more expensive. We do everything by software. And in this case, the one that you are having here, the sensor brushless motor. Let me check the casings. Yes, has 6. In this case, is the traditional way how to do this is we have the coils and we have, I will simplify with just 2, okay? Well, actually we need 3 magnets. What we will do is, and this one, if this one is positive, this one is negative, this one is positive, this one is negative, this one is positive, and this one is negative. So what we do is we install in this motor, let's choose another color, yeah, 3 Hall sensors. Hall sensor is a magnetic sensor. So with these cables, usually they come in a connector. This can have at its own mini processor embedded in the motor, might be in the motor, might not be in the motor. With these guys, we can measure the positions of the magnets and do the same, estimate the position. So actually, we can have position control with brushless motors. Actually, with Romy, Victor is doing this speed, is using an open source speed controller that is not using hard sensor control, is using the one that we explained before, the back EMF control, to actually know the amount of rotations of the motor, to know what is the position of the cable bot on the pulley. Exactly. So you use the most efficient motors.
Yeah, now we have an encoder.
There's an encoder too. Wow. So actually, you can use the most efficient motor, the most weight, like powered by weight rated motor, with less maintenance. Use as a stepper motor. Like basically, you can have the power of this guy. Actually, this guy. Let me see. I know this guy has the same power as this guy in watts. Another thing, for example, this one is designed for speed and this one is for low speed, but you can make the equivalence with half of the weight or even less. And it's all about the electronic control. And what else? Like this is so crazy to do this, like the design of this one. For example, you can have the same motor, just changing the coils. If you buy a motor and you don't like the speed, changing the coils and using a thick cable, for example, you can make it augment the revolutions. Or using a more turns but thinner cable, you can make it be able to go faster. Actually, it's called motor rewinding, and before it used to be quite useful. Actually, big motors, industrial one, they do. When you burn a motor, they rewind the motor. It really doesn't deserve to buy a with the small ones, now it becomes so cheap that it really doesn't deserve. Quite interesting to look for YouTube videos on look for motor winding. It's quite interesting the mechanics on the machines that when the motor is super amazing. They do it at super high speed. Okay, so BLDCs. There is a fifth type of motor that you already went a little bit. That is the servo. Yesterday we went a little bit into the, what is the servo? It was here, no? Ah, because this is not in the main class. This is. The servos of Arduino, what they are inside is the DC motor with the potentiometer and the gears, no? Industrial servo motors is the same concept, but completely different hardware. That is this. So, industrial servo motor, we don't call it just servo, it's servo motor, we need to say the full name to make the difference, it looks like a stepper. It's actually a BLDC, a brushless motor, but has embedded electronic and servo motor driver. So it has the best of everything. So no maintenance, high power by weight ratio, super accurate control, high torque, high speed too. Because of the design, they make it usually in like square format. So that means they have a really good relation between speed and torque. They have encoders. Encoder is to read the positions. There are different types. You have optical one, magnetic one. Usually these guys, the basic ones, at least they have an optical one. Good ones, they have optical, magnetic, and also they can read back EMF. Like these guys become super complex in general. They can do, actually, they can rotate more or less a standard servo motor can go at 1 revolutions per minute up to usually 10,000 revolutions per minute with the skipping the same torque. This is huge. What happened? Super expensive in general. Like nowadays, they're becoming more and more cheaper, but still they're quite expensive. You can, there are some designs to actually cut down the price, and you can find some Chinese providers that they cut a little bit on the build quality of the servo motor, just because these guys are designed to industrial environments. They usually like also like weatherproof, like oil-proof, dust-proof, everything. Actually, this is the motor that, for example, runs inside all the robotic arms. So these guys actually is the same. That a servo motor, like the Arduino servo, but this is like €3. A really good one is €50. A really good one, metal gear, like super high power, like really lightweight, like metal casing. And this one, the cheapest one you can find, I think is €400. But in general, they're around like 1,000 to 3,000 per month. And why the encoder is important? Because in case of brushless motors, like normal BLDCs, like these guys, you can estimate the speed, but you say the speed. And in some cases, with the new generation of speed controllers, you can also read the position, but you are actually sending something to do, reading the position, and the microcontroller is the one that thinks what to do. In case of servo motors, actually, no. They work conceptually in the way you activate them is the same as stepper motors. You tell it the amount of steps. And depends on the type of servo motor, you tell it the amount of steps and the speed that it needs to go to reach that position. So actually, you can tell it, for example, move 10 steps at 1 RPM. You state different things. So actually, with encoders, with servo motors, you talk with a networking protocol. You talk via I2C or industrial protocols like RS485, depends on a lot of the stepper motor, or it's not stepper motor, sorry, servo motor. So actually these guys, they have their own microcontroller embedded and the encoder to actually know the position. Why is important? Because they, on their own, you tell them move 10 steps, the controller is going to move the motor, is going to move the gears. Usually they also can have a reduction embedded into them. They're going to read the position and they're going to go back in the loop to check that they have reached the position. If by somehow the motor has bypassed the 10 steps, it will go back to actually 10 steps. If it has jumped one step, becomes somehow, it will go back to 10 steps. So actually, they are really good to keep the position, to have position control and closed loop control. They're the best of everything. And this is quite important, especially when you have machinery. Let's see a little video of like closed loop control. And yesterday we explained the concept of PAD, no? Control. The servo motors, they have embedded the own firmware. Actually, you can program the motors, you can connect to the computer, and usually they have a suite to configure them, to know the ramp acceleration, speed accelerations, PAD settings, and everything, just in the motor on its own. So the motor
positioning controls.
The motor doesn't become anymore a silly thing. Actually, it's a quite intelligent device that you need to program on your own. So for example, this is the example of what the motor will do internally. And this is about factory calibration also, etc. For example, I have used a servo motor not a long time ago. How it was called? Let's see. Dimension. This guy uses a servo motor that. What is the motor here? Let's see, for example, a data sheet of this kind of motors. It's interesting. Manual and setup guide. Clear path. Clear path, for example, this is a brand that makes servo motors, industrial ones. Technically path motors. Sorry, what's there? They look quite similar to actually a stepper motor, but you can see here, for example, the bus of connection. In general, for example, this one has 6 and has an Ethernet cable to connect immediately, so you can connect to Ethernet, lot of cables, lot of motors between them. Clear path software. Let's just look for the screenshots of the software so you can see. So actually, you can configure, for example, the acceleration curves of the motor and how it's going to treat the desired position and how to acquire the position. If you want to have repeatability, etc. So this becomes like quite extensive to use. They are not straightforward at all.
You need to program the motor and then
Exactly. Yeah, but they are quite significant, the change. Quite significant. With the same size package, you can get like 3-4 times more power. And you get position control, you have alarm systems, etc. So for example, here we have, it's not a servo motor, it's something in between. This is a stepper motor. So we simplify in the mechanical design that has the stepper driver embedded, and has encoder. So actually behaves as a servo motor, but mechanically it's a stepper motor. And that's why here, for example, we can use it as a standard stepper. I don't know if you can see here. We can use, let's see, yeah, we can use, sorry, here. Let's take this out. We can use this guy as a standard stepper, pulse, direction, enable, but we have more. Alarm, for example. If we have lost a step, this will give us a feedback. And bed, I don't know exactly what it is. We haven't gone so far with this motor. But for example, we have TX and RX, so actually we can control by serial this motor with a microcontroller. And we have then like possible like switches that this is for the microstepping. This is kind of a approach to a servo motor, but with the mechanical part of a stepper motor that it makes it easier and cheaper. That's why, for example, this guy is only like 150, 200 euros, but it still has a lot of torque. Also because in this case, it's a NEMA 23 ultra long one, high torque. Actually, this one, if you speed up, last time, do you remember, it jumped from the table. In the moment we switch it on, it just jumped again out of the table. It just has a lot of torque. But what happens? It's not a servo motor, so it's super heavy. Then let's jump a little bit into, for example, we have also DC motors with encoders. In this case, what is an encoder? Encoder is a device that rotates with the motor direction. In this case, it's a metal part, and we have a magnetic sensor to actually count the total amount of rotations. We don't need to have really expensive hardware to know the position. We can use a standard DC motor with an encoder, and they usually look like this. These DC motors are usually designed for low speed. So actually, when you have an encoder, usually you also have a gearbox attached to it, because you want to use that DC motor for low speed applications. So you want to measure the speed rotations. So actually, you can have position control with them. It's the cheapest way to have position control without any motor. To use a DC motor with encoder. And these guys, they can be opto, or they can be magnetic, or there are different types. Encoder, they usually look something like this. On the exterior part of the design, they have a small circuitry. In this case, this is one is magnetic. Let's look for an opto one. Yeah. Basically, it's an LED source, a light sensor, and a black and transparent like disc. So when the light passes through, we measure and we know that's one step.
For this to see if you want, you know, in depth in the room, they have a lot of class in the racks. We do a small workshop in October, November. We disassemble a lot of machines, and all of them are printers. And if you want to go upstairs and see, there's a lot of printers that have encoders in them. And you can take some and see them. If you want to just get some components from out there, there's a small bazaar. If you want to try them and see, even it can be your input or something if you want it as a component if you want. If you feel like that.
So we are in class. This one, I think it doesn't work. Right. So actually, this, for example, is an encoder. It's, as Oscar say, it's a really cheap way to have like really. A DC motor is good. Like it's not a bad device. It's a device that has some constraints, but you can have position control with some like low cost hardware and still perform. Actually, it's widely used in household electronics. And they also can look, for example, like this. You can make your own encoders. It's not too tricky. It's tricky to have like really good position control, but making an encoder to measure the amount of rotation is something that is quite affordable to do. Usually they have, like, for example, they can have, in this case, it's a magnetic Hall encoder because we have encoder A, encoder B. Why? When we are rotating, we have a sensor here and a sensor here, and in this case, it's because of the disc is magnetic. So actually, imagine that we have 4 poles, and this guy is rotating in this direction. So first, it passes to this one, and then it passes to this one. So actually, we can know also if it's rotating clockwise or counterclockwise. Not only know the rotation speed, but also in which direction. So usually, they are designed with 2 output of encoders and ground and VCC. And these guys, they have libraries already done for using them in Arduino. Quite straightforward. Then we have LiPo batteries or lithium batteries in general. We have different types. And probably, well, most of you are around, like, we are from the same age. So probably you have a toy or a car electronic toy that has like big black box of battery. That is a standard lead acid battery. That is the one that is on all your cars. These batteries are really good for having capacity stored for a long time. They're long-term storage, really good ones, but they don't have what is called like high capacity of supply. They don't have high capacity of supply of battery, and they are really heavy. There are different types of these batteries, where you have like the nickel cadmium ones, the nickel NH, I don't know what stage for.
Nickel metal hydride.
Nickel
metal hydride.
Hydric, and then we have what we have nowadays as more or less standard in most of, especially electronic devices, household electronic devices, that is the Li-ion, LiPo, or Li-ion batteries that are like based on the lithium. Those ones, in general, they outperform all the batteries in amount of density of electricity stored by weight, but they have some constraints. They are more sensible to use. So, for example, what do you know about batteries first? In general, yes, it's everything. Well, they are difficult to dispose. They are all based on chemistry. Depends on some of them. They are more nasty than other ones, and other ones can be recycled, and other ones not. That depends a lot of technology of the battery. But you remember that before they say you should not store your battery never fully discharged or never fully charged. You need to be discharging and discharging the battery. Maybe you have an old laptop, you will need to take the plug, let it discharge, and charge it again all the time. Yeah, exactly. That's the memory effect. That is only for nickel cadmium and neon NH batteries. So these batteries, if you keep them at a charge constantly for a long time, their global capacity gets reduced. So actually, those batteries have a memory effect.
So, memory effect?
It's called memory effect. The lead acid doesn't have that one, but what happens is you have bigger and bulkier batteries for the same power amount of electricity it stores. Then we have the Li-ion. We have lithium C, lithium P, but it's like Li-ion and lithium polymer. That outperform all the batteries in capacity. These batteries, all the batteries, for example, a lithium that is a 12-volt battery, in general, the 12-volt battery doesn't exist per se. What we have is cells. So a cell capacity is the minimum unit of a battery in the standards of the market to have a volt. For example, the nickel cadmium battery, probably you remember that they look like this, like similar to a battery with a different size. No, this is the cell. So one cell of a nickel cadmium battery actually is 1.2 volts. How you make 12-volt battery? Connecting them in series. And we do this with all the type of batteries. In case of nickel cadmium batteries, they come in different capacities, different milliamps or amps, depends on the unit or the size of the battery, the total capacity of amps per hour of the battery. And that comes that if a battery is 1 amp, we always consider that it can deliver at 1 amp at a time. We cannot ask it for more. So a 1 amp battery can deliver 1 ampere per hour. No, exactly. You will damage the battery. But it's about charge and discharge rate of the battery. So that is what is called 1C also. It's not about cell, this is about discharge rate of the battery. So 1C is a different C. Yes, exactly. We don't say seal for the cell count, we just say cells. 1 cell, 2 cells, 3 cells, 4 cells, 5 cells, 6 cells, until 48 cells, whatever. And then we have C, that is this also state as discharge and charging rate. So the lead acid, nickel cadmium, Leon, and actually lions, a lot of them, in general, we always work with 1C. Your capacity is actually determining the maximum amount of pool that you can have per hour. Batteries, even so, they like to be used at lower than 1C. It's like 0.8, 0.7, and especially charge slowly. They like a lot to charge slowly. What do you mean they like? They last longer if you do it. Then you have batteries that are like 10C. For the same type of battery, you can have it 10C. That means you can multiply 1 ampere per 10. You can pull 10 amperes in this battery. That means it will last still 1 hour. No, it will last 10 times less. 10 times less. So you can, let's say, use them or draw current faster, but they will still have the same amount of electricity stored. LiPo, and Leon are similar, but they are not exactly the same. They work chemistry-wise, they work in the same similar concepts, and the fabrication is slightly different. So the Leon is what we have as this look like a big AA battery, and these guys, as the table says, is like they have higher energy density than what we have the LiPo. LiPo, they actually look like they are in a bag, in a metallic bag. If you look at one cell, actually up here. Yeah. This is a 1 cell LiPo. This is just one bag. In case of LiPos, the bag is the cell. So this bag is the minimum unit of the LiPo. And this bag is rated, for example, for 2000, sorry, it says 2000 milliamps. So this bag has actually the same capacity as this one, but the form factor is completely different. If one is really thin, one is round and bulky, what will be the difference? For example, this one likes way more than this guy the energy stored for a long time.
Can you translate that?
These ones can last longer, basically last longer. They have more cycles. Batteries, you have what is called cycles. It's total amounts of charge and discharge that the battery can have. That's why, for example, the phone batteries, they run out, they start taking, they last less in the day as long as the time passes fast, because the cycles are making the battery getting damaged slowly on time. They don't have they lose amount of total energy that they can store. So lions in general are more stable. They are more safe because they have a hard packaging, so it's difficult to damage them. If you hit with a hammer, you probably will break it, but with the hands you can't. Meanwhile, the LiPo is actually a aluminum foil plastic sleeve that you can bend with your hand. What happened with Leon and lithium batteries if they touch air? Lithium reacts with the oxygen of the air and starts a chemical fire.
Oh.
So actually, that's why you remember the Samsung phone that exploded. Phones have this kind of batteries. Why? Because they are lightweight, way lightweight than these guys. But they have a slightly higher density energy stored than the LiPo. Lithium can store more energy per weight than LiPo, sorry. So we use them in phones because phones we want them light. What happened, for example, was quite funny, but in the design of the phone, it was not a battery problem, but was essentially how a phone looks inside. In this case, they have two batteries connected in parallel to actually match the form factor of the phone. What happened in the case of the phone Samsung that they start burning is they design it half millimeter shorter the space, or like 1/4 millimeter. So when the battery was completely charged, the battery expands a little bit. That made the metal sleeve back being pressed to a sharp corner, make a puncture, and explode. So actually, these are sensible. If you puncture them, they usually tend to explode. Depends on the type of battery. Um, let's not get too crazy into these kind of things. But if you have more, you want more low slanging, and you don't care about weight, Leon and safety. If you want to outperform weight in general, you want LiPo.
In the package that can change, like lithium ion package can be like lithium polymer,
No.
lithium flat.
No.
Okay.
No, in general, no. These guys, they become in different sizes, but the standard one in the industry is the 18650. That is the measures of the cell, actually. I think it's 118 by 65 or something like that. There are other ones that are shorter than wide and wider. Meanwhile, LiPo, you can find them in a lot of packages. You can have really thin and small, or you can have them like almost square with the same. And these ones, they become in all kinds of shapes and sizes. That's why they are widely used, because it's really easy to customize them. Because basically how these guys are inside is a piece of lithium on paper with a chemical, I don't know what is a reactor, that is also on paper. So basically these sheets of material just stack making a sandwich, and they can cut on size. So actually you can customize your batteries really easily. Meanwhile, these guys, I think they are rolled around like a wrap. So they are not that customizable.
Cars, lithium polymer, yeah. The battery for cars, electric cars.
Electric cars,
Lithium polymer.
no, because you want more energy. What's the problem with car battery? Range. Which one can store more energy? Lithium. Also, and in case of cars, have you seen maybe like some Tesla accidents that the cars are on fire? Because the car batteries usually are on the bottom part because they are really heavy and bulky. Usually they have a really thick metal part protecting them, so something hits on the back, doesn't. So actually you want not only the car to be designed to actually be bulletproof in that sense, but also the cells to be less possible damage. Also in case of car accident, you want that the car explodes with you inside. That this is what will happen with lithium polymer. Actually, the new firefighters, actually nowadays they have to make their own safety guides on how to treat electric cars after an accident, because they need to keep it in store control for like 3 or 4 days after the accident, because the batteries have happened that they start on fire 3 days later. And you cannot just pour water on top of the battery, etc. They have some constraints. So LiPo battery in general, if you want to go higher on the voltage, they look like this. They stack cells instead in series. It's the same package that they just glue on top of each other, and you just alternate the terminals to get more voltage. So both Leon and LiPo, they have the same working voltages. It's slightly different, but let's consider they have the same one. Okay? And they range between what and what? Any idea? 3.3 minimum charge, 4.2 maximum charge. If you go above 4.2, they explode. If you go above 3.3, they might explode or get permanently damaged. They are really sensible onto this. Really, 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 really sensible to this. And especially with overcharge. They start inflating, and when the package cannot resist, they just explode and make a chemical fire.
So those batteries, like the one in Leva,
That's why these batteries we give you with a board. That board has an IC Lion controller that controls this from
but I mean,
happening.
if we let them and they discharge after some time.
They tend to store the charge quite well. So they don't have self-discharge in general. For example, a lead battery has self-discharge way more than a lithium or lithium battery. But even so, they self-discharge. They have a minimum working voltage that is let's say this is the first warning. Second warning or third warning directly. If you go below the 3.0 threshold, the batteries will be damaged forever. You might be able to recover it back to the working voltage, but it will not be the same battery anymore. It will be not be able to store it will be really unstable. Can have battery and suddenly have a super fast discharge. These batteries, we need special controllers in order to charge them. We cannot just plug any charger and connect them. We need to have like charging rates and discharging rates. We have controllers that actually the board you have is doing everything for you, that they don't charge in a straight line, but actually they control the charging rates, depends on the voltage range that they are in. So usually when we are reaching the higher part of the charging one, they start charging slowly. Also, for example, there are some lithium and lithium batteries. They always, in general, they are 1C. But the point is nowadays we make better and better batteries. And for example, this one it doesn't say, so we state is 1C. This one is a 2,400 milliamp battery. So that means we can pull 2.5 amperes, 2.4 amperes continuously. That's quite a lot for a battery this size. Meanwhile, for example, at that voltage, but if we connect the batteries in series, we have 3 cells. 3 cells, 4.2 per 3, how much it is? 12.6. Actually, this is a 12.6 battery. What is the minimum voltage of this battery now? 9.9. 3 cells per 3.2. So actually, if you use this battery of the 3.3, it's quite good. And this battery, for example, is the same as this battery. This is almost. This is 2.4 amps. This is a 2.2 amps. And this is also a 3-cell battery. But the weight, if we have a scale, this one, I don't know, but it's almost double the weight. Not almost, but I will say, I don't know, maybe this is 100 grams and this one is 150 grams. But this guy, in general, the LiPo, they have more discharge rate. That means LiPo, you can find them in 1C, 2C, 3C, 4C. I have batteries that are like 90C. So actually, this one, for example, is 35C. So that means with a 2.2, let's say 2 amperes, this one can provide 60 amperes per second, per hour, sorry. That's a lot. And they have also not only constant discharge rate, but they have also peak discharge rate. That means for a few seconds, they can't even afford one. This one is 120 amps. I have switched on my car with this battery.
Your car?
My car, yeah. I have done like 4 or 5 times. The car it was out of battery because I didn't use 4 months. And I have connected this guy and start my car with this battery.
Actually, the other day I bought one starter that was just a battery pack like this. That can they claim that they can crank up to a 6-cylinder diesel engine, which is quite a big engine in a battery pack like this.
I was at 12 volts already. 12.6. The car can resist, like, no problem with that.
It's gonna be charged at any given.
Yes. Also, in the moment you pull a lot of electricity, the voltage drops a little bit. So it's not big. Actually, okay, this has nothing to do with batteries, but for example, is the only approximation that I can have to a battery on use of this type. Yeah. Okay. Okay, this doesn't work really well. Qué bien. ¿Por qué? No me funciona el USB. ¿O qué? Okay, for example, this is just to have an idea. This is a drone flying, has 4 motors, really power demanding. This one flies with a 1-cell battery. This is a LiPo battery of 4.2. It's not completely charged, but you will see that the moment I go really high on the throttle, like push the motor to the maximum, the voltage drops a lot. But when you stop, it recovers back. So actually, high discharge batteries, usually something that you need to prevent a little bit, is how much they will drop from the voltage. That never goes at any point below the minimum threshold. Meanwhile, in use, even if they recover back. So actually,
But if they tell you the discharge rate, it's calculated so that you don't go below the minimum voltage, no? And if they give you a high voltage, right?
Yes,
it should be completely
exactly. If you are keeping between that area of discharge rate and rate, everything will be okay. So for example, this is 3.8 right now. So it's going to start flying. The moment you switch to the motor, you see how the voltage is varying all the time. In the moment you pull more, you get some peak that is 3.1, 3.1, 3.1, but it's constantly at 3.3, but in use. But in the moment I'm going to crash now, so you will be able to see. This says, for example, the minimum battery went at 2.99, almost in the limit. These batteries for me are disposable; they're really small. But when you recover back, again, 3.6. They are still in the safe zone. So if you overcome the cease of discharge of the battery, what happens is the voltage would get lower than 3.3 or 3 volts. It's really important. For example, the power banks actually are like this. This is the same as you have, but with electronics to control them. And this one that we have, even for the oldest phones, this is actually lithium-ion batteries in the old format of this type. In parallel. Well, actually depends on the battery pack, but in general, these guys are in parallel, and this one has a step up converter to 5 volts. That is the output of your phone. Okay. Before we went into that, you see this guy is a temperature sensor. So actually, the battery doesn't overheat. Overheating is the first thing of you are making something wrong. Actually, that's the difference between a good power bank and a bad power bank. One of the things is not wrong. It's about electronic management and the quality of the electronics. So actually, this guy is important. So how you charge a 12-volt battery of lithium, lipo, lithium, it really doesn't matter. You see that this guy has 2 big power cords. That is like the main output for the 12 volts, and we can have this guy. That is a parallel port serial connection. So each one of these guys they connect to each one of the cells. So actually, to charge them, we need to charge them individually and in parallel. We don't charge at 12 volts. We have a dedicated charger that is actually is not only charging each one. In general, you want to have a balanced charge. As all the cells are connected, it can happen that one cell is slightly more damaged than the other ones, and it's going to suck all the electricity to it. But it's not going to go to anywhere. It's going to be translated into heat and to explosion. So actually, what the chargers do is they charge you, they charge you, they charge you, they see how they are, and they see which one needs to be charged to keep all the cells balanced. So it's called balancing charging.
And you charge it 1.3 each one, or how does it go?
You usually, for charging, you always want to charge at the rating of capacity of your battery in general. Some batteries can charge at more C, but you are forcing a little bit the battery. They don't like to charge that much. So usually you have a balance board, LiPo, Leon charger. Actually, these chargers not only charge LiPo ion, but they charge everything. LED, nickel, cadmium, they have programs as they are like smart chargers. I'm not sharing the screen, sorry. Share screen. Multi-charge. Look for LiPo charger, like this, look like this. And they have multiple type of connectors for 1S, 2S, 3S, 4S, 5S, 6S, 8S, and basically the charger rates for the maximum amount of voltage that they can charge and the speed of charging. Because these guys, they get quite hot also. And you have a lot of them. Actually, this is the most, it was original branded one, but they copy so much that now it has become a standard of copying Chinese clones, and it works so far so good, has been for years in the market. The Emax V6 is the original one, but now they have like contract fees that are better than the original. But these guys, they have like, they can be super smart, and they have like multiple modes. Usually, these LiPos, what they have is they don't like to be completely stored charged. You want it to have a stored in a mid charge in the middle in 3.7%. For example, at home I have a lot of batteries that in this for 6 months I just keep them in storage mode. So these batteries chargers, they charge, they discharge in case you need. For example, for traveling in an airplane, you need to discharge them for safety, or you should do. You should do, nobody does, but they have a storage mode, balancing mode, charge, fast charge, like pushing a little bit harder, and they don't care too much about the balance because they care about having the battery fast. And they have temperature control, warnings, etc.
Just a parenthesis, some phones have like fast charge, one battery, how does it usually function? And then let's just have it charge the battery.
I don't exactly know.
Or
I don't exactly know. Probably the batteries on the cells are better to allow to have more fast charge rate. But I know that Qualcomm has Qualcomm is one microprocessor manufacturer that has embedded IC control for allowing fast charging. And it's at the same time depends on the wall charger that is able to deliver that amount of power. That's why they are around now. The chargers are 3 amps. That is a lot, or 5 amps, even the newest phones. But it's also about the electronics and how they manage the electricity into the cell. I don't exactly know. I think that it might be by storing them into capacitors and then slowly discharging into the battery, or maybe, but I'm not completely. Like, I have no idea. So always a use a LiPo or ion charger for specific for that. And be careful when you connect directly things to the motor, like the batteries, you can do it. But having an account that you need to monitor in some way the voltage of the cells. Actually, they sell some specific things that is like LiPo battery bar warner.
how do you monitor them to the robot?
These guys that you connect directly to the parallel port, and basically they start beeping at 100 decibels or 90, depends on the charger, if you get below the threshold. And they show you in the little screen this guy. Actually, I think what you do is you monitor the cell with the controller. That is also possible. And making a Leon charger for 1S is quite simple. It's super easy to do it, and we have like different microchips that we can integrate in your final project to actually be able to charge the battery and manage it completely autonomously. So you can connect the battery. You have the Leon, usually it's a Leon controller stick that charges, discharges, and when the voltage is going to load, cuts the voltage. So cuts all the circuitry for everything. I think the most used one is MSCP. Yeah, yeah. Yep. Oh my God, I look it so much. That shows on Google. And the security is quite easy. This is the simplest one. We have more complex ones, so this is the one that you use in smart system, that they do a lot of things. But these ones, for example, they just charge safely your batteries. No sé, Oscar, cuéntame, no paro de hablar.
But what about AC, or it's not commonly used, or we cannot use it?
Just to give you an idea, I finished with the batteries. So the battery starts conflating slowly. Didn't puncture it. Well, it's basically a LiPo battery on fire. The problem with this is a chemical fire. Usually, if you put water, it gets worse. Sand. 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 Put soil over it. And store it in a metal bag, but that is not closed, because if not, it gets spanned and the bag is closed. You need to have a step to compensate the air pressure. This is not that bad. There are way worse ones. This is a fully charged battery. Like basically, this is an overcharged battery. The fire is worse. Why? Because it needs to actually dissipate that amount of energy somehow. Usually, this becomes also the charge rate. High discharge rate batteries, they have more energy density, so actually they tend to have like bigger fires than others. No sé. Ok, vamos.
Pues, ¿tú quieres hablar del PID?
Of PID.
O podemos hablar...
There's a question, okay? What is the question? Question about monitoring how to handle say 100 motors aside from current draw. Carla, can you explain that a little bit more, please?
Yes, well, so basically it's a question for my final project. I might need a lot of motors, and I'm also looking which motors to choose and how to control them in an efficient and let's say accurate way. I need the motor to be precise in position because I have 4 states for the motor, and I need each motor to be controlled individually.
And you want to have like, what is the range of movement of the motor? Is high speed, is low speed, is position control?
It can be low speed, it's position controlled. It needs to be at least, well, it needs to be 270 because I want it to be positioned at 0, 90, 180 and 270 degrees.
I think the easiest way is to go to a chip. Depends on the torque, but to a standard like chip hobbyist servo.
Okay, but do I need to hack it to get to 270?
270. I think there are servers that go from 0 to 270. Maybe not that popular, but don't know right now. But the problem is position control. The moment you have position control, even with a DC motor with encoder, the problem is to have a lot of wire. So in that case, it will be might even easier to do a specific port for each motor to have individual control and go for the modularity side. That you have a network of 100 motors controlled.
Okay, well, maybe we can talk about it further, because like for me, the wiring could end up being an issue, as the electronics will be visible in the whole thing.
Yeah. Another option is take a small DC motor with gears, and you control the positions by the time you spend putting energy into them. It's like a really not that accurate, but if you make a lot of tests and control, you might be able to reach precise timing.
That sounds interesting.
You are always working, let's say, blind, but it's a way to cut down a little bit on the complexity.
But is it feasible to reproduce it? So let's say that I have motor 1 that it's accurate, and I have angle 0, 90, 180, and 270. And then when I do it for the other 99, it will be the same, or do I need to set up all the motors by different timings?
In theory, if it's the same motor, you should be able to almost the same timings. Might be slightly small differences.
Okay, I might try then.
100 motors, a lot of motors.
Yeah, well, I can reduce it at least for the prototype, but I would say that it won't be less than 50, because I'm trying to build a physical, like, mechanical display. So I need many motors.
In theory, like when you go that like amount of elements, whatever it is motor or it is, like networking is usually the smartest one, because you make one module that maybe contains 3 motors, and if it works well and you calibrate it well, it's about just reproducing it, not making a whole system from scratch.
Yeah, I took a look at the servo I2C shields that you can chain one after the other, and that looked promising, but I wasn't sure if I was going to achieve the range with servos, so that's why I was considering other options.
Yeah, the servo shields that they multiplex, no? Yeah, that ones are nice. You can use them also daisy chaining them. So actually, if you have one that comes from 1 to 16, you can have 1 to 16, and from each one of the 16, just you can make another 16 ones. But the problem is also there is like cable distance, amount of cables, wiring becomes complex. You need to be really organized.
Yeah.
Okay.
Thank you.
Welcome. For example, here I have, I don't know what it is. Well, these are examples of different motors that we can have, and we bring it here the power supply so you can test it. For example, especially for DC motors, it's easy. But here, I don't know what it is now. We have, for example, this is a motor of that we can use. This is a ARS 550 that we can use for like the router. That is the one that we use in this Chinese CNCs. It's slightly more powerful. This one, for example, is a DC motor with brushes that consumes more or less 3 amperes. But here, this guy consumes also 3 amperes. What happened? This one is for torque, and this one is for speed. This one is 90,000 RPMs. But the difference size is huge. But this one is thing to move like small amount of loads at really high speed, and this one is to actually do the opposite, slow, big amount of loads at really low speed. I think this one is 15,000 RPM. I don't know. What's that?
Yes, hello.
Sí, sí, PID. Yeah. Okay. PID control. You want to explain? ¿Hacemos la prueba? ¿Lo traemos? Yeah.
2 minutes.
Like we need to leave both at once. So yes or yes is like 5 minutes, gonna be 10 minutes. So PID control. Yesterday we stayed. Bueno, le quiero que lo explica mejor eso. Sí, sí. Sí, 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 sí. So PID control is what is there are some algorithms it's called proportional, integrate, and derivate that they merge together to actually have a great estimate of what is going to happen, let's say, or what is the next steps to move or activate an output based on a feedback from an input. So let's say we want to, basically this is a pellet cell. This side of a pellet cell pulls down and this one speeds up. It's a ceramic tile that when you conduct electricity through it, one side produces heat and the other one produces cold. The only thing you need to care is that the hot side doesn't heat up the cold side. If that is a thermal collapse and the cell basically explodes. Well, doesn't explode, but gets damaged. So what you need to keep is that the hot side is constantly well ventilated. So you can use for cooling or for heating, depends on the side of the room that you want to use. So if this is a heater, or we have the heating pad, that in your case, Gerardo, is quite important, you want to have a target of 100 degrees. When you start heating an element, what you will do, you are making fully on, no? When you reach the 100, you turn on. But the temperature keeps rising. Why? Yes, mass inertia of the material. In this case, because it's temperature. In case of a motor, if you are on the bicycle and stop pedaling, you don't stop, unless you have a fixie. But in general, you don't stop. You keep going. So actually, this is how a thermostat works. That when you go below threshold, it's activated. And usually this it's not instant, takes a little bit of time. You have a range of threshold. So actually, to prevent this, actually what happened finally is that you have a curve of this of temperature control. This is bad. No, this can depends on the system could go on this range. For a house, it's not bad. Depends actually. Well, actually, it's also bad because you are wasting energy and not whatever you want. But what to prevent this, we have temperature and the PID control. This can be with motors or basically any actuation device. That what it does is it prevents, let's say it's an algorithm that doesn't learn because it's not machine learning, but prevents that will have some numbers that you can estimate to know that how much inertia your system has. Actually, you turn off before to reach the point, and it knows not only the amount of inertia, but the time delay on the time expended to actually lose that inertia to turn on whenever it's above, so actually compensates for the drop downs again. So actually you are turning on and off, not on the threshold, but after or before based on your system. So proportional, what it does is fast corrections. Let's say it will be the closest similar to on off when it's close to the threshold. Integrated is ultra fast short time corrections, that the ones that are like done in like 1 second. And derivative sees the whole picture and calculates based on that.
So, can I draw in the thing?
Sí.
So you have to take. So imagine that this is the target that we put in here, and that on the other side we put the error, the difference between the target and our actual measurement. No? So if we plot the error in here, we will see something like the error goes down, becomes negative, then positive, and negative. Etc. So the P is basically acting based on the magnitude of the error. Okay, how much error we have, we multiply that by a constant, a number, 0.5, 1, 2, whatever, and that becomes the action that we put in. Okay. The I, as you can imagine, P can have a problem because when we get to this, we will act less. But when we get to, at this point, our system might have inertia, and we don't have any consciousness or idea, we're not aware that we are actually getting close to this, and we might have a problem of overshoot. And like systems that only rely on high levels of P tend to do something like this, a huge overshoot, and then they never stabilize because the constant value is too large, and it never can set to an actual set point. The integral value, what it does is that over time it calculates the sum of, or the integral. So if you know a little bit about calculus, it's the area behind or between, sorry, under the error, and it integrates. Let's say this is important because some systems might not ever be able to attain value, and they might stay like this, like whatever, somewhere like that, stable, but they have a value, a constant error. So what you want to do is, in the future, this value, if it accumulates, is going to become very large. So you want to act on that, and you want to reduce it with time. So the more you accumulate, the closer to you go, and at the end you stay close to your target, right? And the final is the derivative, which what it does is that it takes into account the gradient of your error and calculates if you are going too fast towards the set point or you are getting close. And this is interesting because you could do something like, if your error is going like this, you're going like that. What is interesting about this is that you can say, okay, here I have a lot of gradient, I'm interested on correcting more. But here, so I have a lot of error and I really want to go fast towards my target. So here I correct more. But as soon as I'm getting towards the target and the gradient is getting less and less, I don't want to keep correcting. I want to counteract the action of the P. And with this derivative, I want to counteract that so that I don't go over it and I overshoot. I just little by little slow down so that I don't correct and I get to my set point in a like smoother fashion. So ideally, the idea is that if you, and this is done like by a frequency response, this is your pulse. So you test your system with infinitely fast pulse, and you say, ideally what I want is to do something like this, right? You don't overshoot, you don't have permanent error, and you do it in a very small amount of time. That amount of time is normally called tau 90 with this Greek letter that basically says what is the amount of time that took me to get to the 90% of our set point. That you might also see at tau 63, etc. And this is a constant of like all control systems, and they will say stabilization time 3 seconds, stabilization time 20 minutes, depends.
But even if we see the curves, the force system is on and off. We just have full blood or not. We are not making an analysis. This is about what is happening in reality on the temperature or on the control of the position. So the actuation is on and off.
And the idea here is that, or the important part here is not only, well, of course, to know what this stands for. There's already libraries and a lot of people that have created a lot of material for you to calibrate this, like tune these parameters somehow automatically, so you don't have to do so much. But normally there's already like rules to do this. But the important idea is that you have a system and feedback, and what you do is that you need to compensate based on the error that you are making based on compensating with your set point. And that is taking into account 3 components that then you sum and then you feed that back into your system. So that's the whole principle of closed loop control, because you have a loop in here that, let's say, gets information from your system and you operate based on it. Yeah.
That can apply to the temperature control. I will be maybe over engineering a bit. No, I don't need such a precise.
It's really important. It's really
No,
important.
because we thought what was the name of the process? That you don't work on the threshold, but you set like a range.
Hysteresis. And hysteresis, yeah. Yeah. So the idea here is that at the end, what you have is a set point, somewhere that you want to get. And in this case, an hysteresis is simply an on and off decision making. And this is more to for control system, let's say, with the idea that you want to forever be stable in this point and actually have a metric that is like infinitely with infinite values and control it with a discrete system. Okay.
For example, this happens especially the more your information is more important. For example,
let's imagine, for instance, that we want to heat up this room, and we put all of these heaters. We put them in here, and we turn all of them on. And we say, okay, I want to heat up the room to this value, and I turn them all on because I think, okay, I'm getting, and get here, and all of a sudden, those we turn them off when we get to the threshold or where we close the hysteresis. But temperature systems, they always have a lot of energy, especially in air and climate. So you're gonna go like this. And then after a while, you're gonna realize that, well, you went over the top and you probably hear to say, okay, I'm coming down again. You will get here, you turn them on, and you're gonna be forever like this. Unless you have possibility to implement something like this that predicts that when you're here already, you should already start closing a little bit. And if you do it well, this oscillation is going to be more and more like that. And ideally, this what is called like permanent or permanent offset or like static error that is remaining after a period of time, you don't have any because of the integral part, which basically penalizes small amounts of error, but during long time, because basically we're accumulating small errors and taking all of them into account, and all of those little by little they grow and compensates in the static error and
the idea already and the in general they have outcomes that they have set those examples that they run your system for a few cycles until actually they find automatically which ones are the corresponding PID.
You have documentation for that?
For example, printers, they use it actually for calibration. It's one of the things, first thing you should do when you buy a printer is run a PID out of them. Actually, for example, usually they make 3 cycles. You want to have good ones that you can run 50 cycles. Actually, you get made. And you get like locked in place 230 degrees of 5 degrees in, for example, the printer makes a difference in the plastic values. For example, the sheet press there, we don't want to have like an image controller that we need to program. Actually, they exist already. PID temperature controller that this is a relay that actuates your heating system based on the temperature target. And in general, they have a auto programming mode that you set up for auto tune. And you set it run for 1-2 hours. You need to be careful because it might overshoot a lot or undershoot. And they self find the value, and they also can state, for example, the steady value. You can go really deep into this. The communication in general of these guys is not amazing. Unless you buy good quality one. But they have like, and actually they can set up for cooling or for heating in case of this temperature control. But doing this, with your IT Tiny, it's basically they don't dispatch software. So actually you can embed the same equations. In Arduino, there is a lot of libraries for auto tune and PID controller.
That's basically what I want.
Yeah, like what you need to make it. For example, the Google that engine there, for example, has two PIDs. Each one with its own temperature sensor. But for example, one of the PIDs is activating 2 heater fans, not this one. And these guys, they also have PIDs. Like servo motor has PIDs, this guy has a PID. Servos, theoretically, inside, they should have a PID. I don't think they will. Maybe good ones, yes. And the ones that are the simple ones, I don't think they have a PID. But who knows what is inside. Yeah.
Apart from motor control and temperature,
There's anything you want to control,
Anything that has actuation.
well, usually when you have an inertia, you cannot control, or anytime you control something.
no, basically anything you want to control. Like imagine, I don't know, a classic control theory example is the inverted pendulum. That you have like a pendulum that is like this, that you want to, with only like one axis, to control it vertically. And the motor is gonna start like doing like this, and it's gonna go and do this now. And it's just one axis, for instance. But this doesn't have inertia, but it's very unstable. As soon as it does a little bit like that, it falls down. And it has to learn also how to bring it up. And stays there. Like, theoretically, this doesn't have any inertia. And this is the same principle. I don't know if I'm saying something stupid, but to compensate like how like the verticality in aviation, things like that.
No. Actually, it's impossible to fly with a PID. Impossible.
So-
Actually, like I've been doing drones since more or less they become affordable in the hobby way, like 10, almost 10 years old now. Like the first one is an Arduino, and with the first equation of PID, they were like quite awful, and it was everything about finding the PID, and the auto tune didn't exist. You need to find it your own, and actually in drones it's quite easy, like because you can actually see if the drone is doing like this, really unstable, augment your P. Too much overshoot, physically the drone does like this. That you increment the D to stabilize on time. So actually becomes less responsive. Increment your I has like overshooting, so super high frequency vibration, for example. In that case, you reduce your augment your P because the P reduces the I at the same time. It's a balance. So you augment your P, you augment your D, then the I gets well, and that's how you tune. Like in some like physical examples, this in temperature is really difficult to see, but mechanically, it's quite easy to see. And there's a lot of really good. There's a really good video explanation of PID with a pendulum. PID. This one is really good. This one, for example. This one shows a system with just P. it's trying to correct, but doesn't know exactly where to correct. So as long as you integrate the different you see it's overshooting a lot. But with just the D, it doesn't get exactly to the position. Like having a system with like normal hysteresis control and having the PAD is like the unknown on like how good is the control. And like having accurate, let's say, tuning of the PAD is not that straightforward, but having a more or less stable system with PAD that usually like works flawlessly compared to hysteresis is really easy to integrate with libraries. Yeah, that's yep. Hope you like it. Here you have a lot of examples to try. For example, this guy is just an octocoupler. This is just a board with octocouplers. This is a 5-volt line, and this is a 24-volt line for industrial robots. Well, this is an industrial shield. This is 24-volt data line, 5-volt data line. You want to have isolated, so these guys are actually octocouplers. And this is to get that if this lights, it means we get data in, and this one gets data out, just to have visual confirmation that this guy is working well.
So you set the maximum enter, and then when you start, it shows the one it's consuming.
Exactly. So actually, the power supplies you can set up the voltage, okay, and you can set up a limit in the amperage. Okay, so don't overrun the motor. Okay. In this case, the motor is going to start whatever we can. For example, this power supplies are rated 1 maximum amperage output of 3.2. This one is a 5 amperage maximum output. So change your voltage, that's in the consumption until it reaches the maximum, but in that case the voltage will drop. Right. This motor consumes more than. Also, right now it doesn't have any load, so it's not consuming a lot.
You should break it.
I don't want to break it in that time. You see how the amperage consumption rises super fast.
So the output starts and final receive.
So this possible is better than this one, but I don't know how.
Okay, nice. There's no more questions on the online side. There is? No? Okay.
Thank
It's good.
So, see you.
So,
So,